Let's just get a little bit of practice right here. A fish is kind of sitting there and it makes itself more dense, then what's going to happen? So there's kind of our fish, and it's going to make itself more dense, so it's going to, kind of go from that guy to that guy. Obviously this fish takes up less volume, so it's more dense. Remembering that density is equal to mass divided by volume. So essentially what it's done is it's made its volume smaller. So the buoyant force on it is going to decrease because the buoyant force is equal to the density of the fluid, the volume of the object multiplied by gravity. And what the fish has done is it's decreased its volume and decreased its buoyant force, and so it's more likely to start to sink. Now, I do know that we're talking about liquids, but let's just talk about gases for a second. I mean, hot air balloons, how do they work, and is there going to be a height limit? Essentially how they work is going to be Archimedes' Principle, and essentially what a hot air balloon is doing is it's displacing some air with something that's less dense. And what it works is, buoyant force is going to be density of the fluid multiplied by volume multiplied by gravity, and the density of room temperature air is going to be about 1.2 kilograms per cubic meter. The density of hot air is going to be much less. It's going to be about 0.94, and as long as the density of the hot air is less than the density of the air, then it's going to rise, and the more air that it displaces, the larger the buoyant force. So if it displaces its weight in air, then it's just going to kind of hover there. If it displaces less air than what it weighs, then the hot air balloon is going to go down. Now, how about helium balloons? Well, the density of helium is much less than the density of air, and so we can get a really large buoyant force on this guy for a small amount of volume, and there's kind of me launching some radiosondes, which were helium-filled balloons. Now let's get a little bit of practice with the buoyant force, and this used to be a test question, but not a lot of people got it, and so it was kind of cool, so it's not a test question anymore. But you have three spheres that are made of different materials, cork, aluminum, and lead, but they have the same radii, very key, and they're all totally submerged. Compare the buoyant force acting on them. We're calling it the buoyant force is going to be the density of the fluid, not the object, multiplied by the volume, multiplied by the gravity. And in this case, all three objects are in the same fluid, so the density is going to be the same. Even though the density of the objects are different, this is the density of the fluid, not of the object. The volume is the same, they're all the same radii. Gravity is the same, so actually the buoyant force is all going to be the same. Now, Archimedes' Principles actually explains, how submarines can kind of go up or down in the water, and the way that a submarine works is it has these ballast tanks, and kind of outlined in blue right there. And those ballast tanks, you can either fill them with water, or you can fill them with some compressed air. You can kind of see the ballast tanks kind of surround this guy. And if you want to submerge, then you're just going to fill these ballast tanks with water. Essentially what you're doing is you're increasing the density of the submarine, which is reducing the buoyancy, so it's going to go down. Turns out that you can match the water density with a water-air mixture to stay at the same level, so the buoyant force will be equal to the weight. And if you want to float, then you just pump these ballast tanks full of air. What you're doing is you're decreasing the density and increasing buoyancy. Now I want to finish off with the last concept of the chapter, which is going to be Pascal's Principle. And what Pascal's Principle says is if you apply pressure to a liquid, then it's going to go to every part of liquid, or to every surface in the liquid. So if you had, say, the atmosphere pressing down on a tank of water, then that pressure is going to go to all surfaces, so it's going to go to that surface, that surface, that surface, that surface. And if you had an object in the water, it's going to go to that surface, that surface, that surface, and that surface. Now, practical application of this is, people talk about shooting fish in a barrel, so if you had some fish inside of a barrel and you were to shoot it, then, so these are going to be my bullets kind of going in. It turns out you don't actually have to even hit the fish. The pressure wave that is set off by all of those bullets impacting the water is going to go to all surfaces, including the fish, which have very sensitive gills and organs, and that's what's going to lead to the end of the fish. So it all boils down to Pascal's principle. Now I have two examples of Pascal's principle in action. Here I have a little Cartesian diver is what he's called. He's slightly less dense than the water. I squeeze the bottle and he becomes more dense than the water and he sinks. I let go of the bottle and he expands and he floats. Squeeze the bottle, he goes down. Release the bottle, he goes back up. Here's an example of something that is not Pascal's principle. People said if you fill a bottle up with water and you hit it on the top, then Pascal's principle just takes that force down to the bottom. However, you see I'm pouring some out. What's up with that? But water has inertia. You hit it, it hits the top of the bottle and comes crashing down on the bottom of the bottle, and that's why it actually finally breaks. Now, an application of Pascal's principle is going to be how a hydraulic press works. For example, if you take your car into the garage and they lift it up using hydraulic press, what they're doing is they're actually taking advantage of mechanical advantage. So you could have a relatively small weight on a relatively small area, and essentially the pressure right there has got to be equal to the pressure right there. That's what Pascal's principle says. If you apply pressure right here, it's going to be the same as the pressure right here. Well, remember that pressure is going to be defined as the force per unit area. So essentially what we're saying is the force per unit area on this side has got to be equal to the force per unit area on this side. And on this side right here we have a 10 kilogram mass in an area of just A. So this is going to be the 10 kilogram mass multiplied by gravity. And right over here is just going to be the area. Now the question is how much can we lift up? So what is the value of F2? Well, this is going to be 50 times the area. Right there it's 50A. So when you go ahead and you set these guys equal, you're going to have 100 divided by area is equal to F2 divided by 50 times that area, and the areas are going to cancel out, and so this F2 is going to be equal to 50,000 newtons, or 500 kilograms is going to be the mass that it can lift up. So we can lift a very massive object with a small object. Keep in mind that the work has got to be the same. So if this guy right here goes up an inch, this guy right here might have to go up and down about a foot or two.